Hi everybody, welcome to this lecture 4 of week 7 on linear systems theory. So far we had derived conditions for controllability. We had also checked equivalent methods starting from the PBH test to the eigenvector test. Is there any relation between Lyapunov stability and controllability and so on. So this lecture we will talk mostly about discrete time systems. Discrete time systems, well, they are usually given in this form: x k plus 1 is a k, x k plus b k u k for some m dimensional input. So how does one define for here the state transition matrix? Okay, we start with systems of the form let they be depending on time, like the A and B matrices are also depending on time. Okay, so how do I go about computing the solution of this or even the state transition matrix? Very similar to what we had done earlier. So let us start with k equal to 0 and check how the solution looks like. B naught u naught. Similarly, I can compute x of 2 as a 1 x 1 plus b 1 u 1. So this is what is x of 1. So this is a naught x naught plus b naught u naught plus b 1 u 1. So this is a 1 a naught x naught plus a 1 b naught u naught plus b 1 u 1. Okay, so so in general, so if I call this as my state transition matrix, I can write it write a general expression for this, right. So and then x at k1 will be equal to x1. Okay, so again the notion of the reachable and the controllable subspaces remains the same. So we will just see what, just read out these statements again. So given 2 times k1 which is greater than 0 and k naught can be equal to 0, the reachable subspace consists of all states x1 for which there exists an input sequence, right. So the reason why we just need this input sequence, if you look at here is okay, to define x at 2 I need u naught and I also need u1. Okay, so I need this input sequence that transfers the state from xk0, like this is the origin, to some state xk1, right. That is the set of all possible x1s for which there exists a control which can solve for this equation. So this is just by substituting x naught equal to 0 in this expression. Similarly for the controllable subspace, so I have given 2 times k1 with the same conditions. The controllable subspace consists of all states x1 for which there exists input sequence that transfers from any initial condition to the origin. So it's just by looking at, okay, that my final state is the origin. So I have a 0 on the left hand side and that would just turn out to be something like this. So all the initial states x naught for which there exists a solution to this equation, right. So to something. So if I were to just find out in this case of 2, so I am just say what is so here I have 0 is a1 a0 x naught plus a1 b naught u naught plus b1 b1 u1. So I am finding a solution for this u for all possible x naughts. Okay. So that is what this expression says. I think there is an x naught missing here. Okay. In the very similar way as that for continuous time systems, we define the controllability gramians, right, which will be useful for us in checking the conditions for controllability. Okay. So there is a slight distinction when we translate from the control time systems to the discrete time systems. Okay. So what is an important thing here to observe is that the definition of discrete time controllability, it requires backward in time state transition matrix from k plus 1 to k naught. So if I just look at the first expression, so in general x k plus 1 can be written as ak minus 1 all the way till ak naught times x naught. And I can solve for this x naught if and only if all these a's are invertible or they are non-singular. Okay. So we will again come back to what this means. What happens to the gramian in case these a's are singular matrices. We will discuss this again when we look at LTI systems, so that we can actually fit in and compute it very nicely and interpret what these statements could mean. Okay. So the first theorem is very easy to check, is that the reachable subspace is just the image of the reachability gramian in the discrete time case, and the input that steers my state from the origin to any x k1 is just given by this expression. Similarly, I can do for the controllability test also, right. So if so the controllable subspace is the image of WC, essentially means that I am just just taking all the set of points that can be reached from the origin, that will be just the image of this WR here. Similarly, for the controllable subspace, the proofs are very similar to those of the continuous time case. So I will skip the proofs over here. It's exactly the same steps. Okay. So here, well, what is the notion now of a controllability matrix? Okay. So we start with a discrete time system. Just for ease of notation, I just write it x plus, instead of xk plus 1 is axk and so on. Again, I just switch to linear time invariant systems. Now in this case, I have the gramians defined respectively in the following way, and the controllability matrix remains the same. Okay. So let us reinterpret this statement here. So what is the definition of a discrete time controllability gramian? So here let us say, okay, I am just interested now in these powers, right, a k naught minus 1 minus k. Okay. So when k equal to k naught, the first term becomes a k naught minus 1 minus k naught, that is a inverse. Similarly, in the second time step, I have k naught plus 1 is a k naught minus 1, sorry, minus 1 minus k. So what is k is now? K is k naught plus 1. So this is a power minus 2 and so on. And therefore, you see that there is some requirement for the invertibility of A, right. So this is what it means here, right. So all these matrices are non-singular, and if this does not happen, the gramian cannot be defined. Okay. So this a little distinction between the continuous time and the discrete time evolution. No such problem though exists here. So here we are kind of okay. Okay. So the next theorem says that, again, given any two time instances with k1 satisfying this, I will tell you why this is important. We have the similar theorem, right, that the reachable subspace, which is equal to okay, it should be the image of WR is the image of C. So, this will be the image of the controllability Gramian, which is equal to the controllable subspace. Okay, so I will do a part of this proof, and the one which is obvious I will just leave it as an exercise. Okay, so and then also we also look at why this particular thing here is important. Okay, so what is to be shown is the following, right? So R T naught comma T1 is the image of WR, sorry, just do in the discrete terms is K naught K1 K naught K1, this is image of C. I will leave the other proof, I will just do this part of the proof. So, what is easy to prove is the following. So, we start by showing, okay, the first step is if x1 is in the reachable subspace, then it is easy to show that this x1 is also in the image of C. So, what is C is just the controllability matrix B A B till A n minus 1 B. Okay. So, this part is easy. So, we will show the converse, that if, so assume that x1 is actually in the image of C. Okay. Now, we have to check if this actually means that this x1 is also in the reachable subspace, which is nothing but the image of the reachability Gramian from K0 to K1. Okay. Now, when x1 is in the image of C, which means there will exist a vector, sorry, vector V, which is in R m times n, such that, okay, what is the dimension of this? So, this will be of dimension n cross m n, such that x1 is C times V. So, this is B A B A n minus 1 B times, let us define these vectors B naught till V n minus 1. So, this is summation, be a transpose here, summation I equal to 1 to n minus 1 A I B V I. Okay. Okay. How do we understand this? So, whenever we talk of discrete time systems, we talk of the n step control. Okay, what does it mean by the n step control? So, let me just write down a simple equation here. Xk plus 1 is A xk plus B uk. Okay, so what does this do? So, I have x1 is A x naught plus B u naught. Assume for simplicity here that u is just a scalar. Then x2 is A of x1 plus B of u1. So, this is A okay. So, this is A square x naught plus A B u naught plus B u1. Okay, and similarly I can write x of 3 is a cube of x naught plus so x of 3, okay, just let's write this x of 3 is a x2 plus b u2. So, this is what is x of 2? X of 2 is a square x naught plus ab u naught plus b u1 plus b u2. So, that will be a cube x naught a square b u naught plus a b u1 plus b u of 2. Okay, so let us just assume that n equal to 3 here. So, this is a cube x naught plus we will have b a b a square b times u2 u1 u naught. Okay. So, when we do the controllability, so this is my C matrix. Okay, here I am just assuming that this u is a scalar just for ease of understanding here. So, the controllability would mean that I should be able to reach any point x3 is say x of 3 starting from the origin. So, let me assume that this is the origin, then it should mean that this C is invertible, right. Okay. Now, this is like the 3 step Gramian. So, I have this step 1, step 2, step 3. So, in general I talk of the n step control. So, the idea here is okay. So, if this is controllable means C is invertible and I can control the system in say 3 steps, or in general this is n steps. Okay. So, if I cannot control the system in n steps, can I control? So, I will just write this down. If the system is uncontrollable in n steps, can it be controllable in n plus 1 steps? Okay. So, let us look at it, right. So, then my controllability the Gramian that I compute, sorry, the controllability matrix would be b a b a square b and say a cube b, or in general this would be just a n b. Okay. But what do I know from the Cayley-Hamilton theorem, that this a n b or a cube b in this case can be written as a linear combination of these 3, and therefore, this does not contribute to the rank. So, if it is controllable in n steps, it is controllable. So, and if it is not controllable in n steps, it cannot be controllable in n plus 1 steps. However, there are possibilities where it could be controllable in some k steps which is less than n, for example. So, I will do an example with this. So, this is the idea of n step control, and that is where the Gramian comes in, right. So, we compute the Gramian for n steps, but if I go for n plus 1, it does not really add anything to my control or to my controllability properties. But what does it also go on to show is that I must compute this for at least, so I must let the system evolve for at least n steps, right. So, this is step 1, step 2, step 3 in this case, because here I am just for simplicity assuming it is R3, even though you could just generalize it for n dimensions. Okay. So, okay, back to here, all right. Okay. So, what we have to show is now that the control at least goes on for n steps, and therefore, I can write u of tau now as being 0 for t0 less than or equal to t less than t1 minus n, and this is v T1 minus 1 minus tau for T1 minus n less than or equal to T1 minus 1. Okay. I'll quickly explain what this means, but just let's write down complete the proof first before we understand this. So x, okay, so I should do a k here, it's because I am talking in discrete times. So this is sorry, v k1 minus 1 minus tau, this is k naught less than or equal to k, k1 minus n, this will be again k1 minus n is less than or equal to k, which is less than or equal to k1 minus 1. Okay. So, x at T1 is summation tau equal to say k naught to k1 minus 1 a power k1 minus 1 minus tau b u tau. Okay. So, now this tau is 0 from k0 to k1 minus n. So, I just start from here, right. So, this is equal to summation k1 minus n to k1 minus 1 a k1 minus 1 minus tau b v t sorry b v of k1 minus 1 minus tau. This is simply I equal to 0 to n minus 1 a power I b v I. Okay, what do I know of this? What do I know of this? Because I know that x1 is in the image of C. So, I will get x1. Okay. Okay. Now, let's quickly understand what these things mean. Okay. So, one way to understand this quickly is let me assume that k naught is equal to 0. Okay. And what do I need for control is I need to go at least n time steps. So, this is k naught plus 1 all the way till k1 in such a way that that this should be n, right, that k1 minus k naught should at least be equal to n. Right, that is what this expression says. And why do I need at least n time steps is for to compute the controllability matrix. Okay. Now, okay, so this is one way of looking at it. Now, if I just look at k naught equal to 0 and that k1 is such that k1 minus k naught is at least greater than or equal to n, then let us look at how this expression translates to. Okay. So, what is the expression that we have? Okay. So, I have u of tau, the way I write it as 0 for k naught less than or equal to k less than or equal to k1 minus n. Then I have this u is v k1 minus 1 minus tau for k1 minus n less than or equal to k less than k1 minus 1. Okay. So, when let us say k naught equal to 0 And what do I need? I need, so what do I have from this expression here is that for the n step Gramian is k1 minus k naught should be at least equal to n. So, k1 minus k naught, let me just assume this is n. So, I have k1 equal to n. Okay. So, this is 0, right. The first one is anyway 0 because I have 0 less than or equal to k less than or equal. So, this is a strict less than here, less than 0. So, this is ruled out. So, the second expression will say that okay, what is so for from 0 less than k less than equal to n minus 1, I will have the input v as okay. Now, I have k1 minus 1 minus tau. What is k1? This is n minus 1 minus tau. So, I have v n minus 1 minus tau. Okay. So, that is what I have on the right hand side here. Okay. And therefore, now to look at, so this should be now a little easier to look at because k1 is equal to n. So, I just look at the summation from 0 till n minus 1 and then they just translates to a power I here, right, and then you compute backwards from n minus 1. So, okay, let us look at this summation part for a while. So, what do I have here is summation tau equal to k1 minus n to k1 minus 1 a power k1 minus 1 minus tau b v of again k1 minus 1 minus tau. Okay, what do I know? I know that k1 is equal to n. Okay, so, this will be summation tau equal to 0 to k1 to n minus 1 a power n minus 1 minus tau b v n minus 1 minus tau. So, when tau equal to 0, I will have a power n minus 1 b v computed at n minus 1. When tau equal to 1, I will have a n minus 2 b v n minus 2 all the way till a power 0 b v 0. That is what was here, right, this one. Okay. Okay. Now, what does this lead us to observe or to conclude? That in discrete time the notions of controllability and reachability coincide only if the matrix is singular, right. Otherwise, well, that the reachable subspace is or the reachable set is a subset of the controllable subset, but the reverse inclusion does not always hold. Okay. So, the second thing which we will derive with the help of an example is that in the discrete time the notion of controllability and reachability do not depend on time only when the intervals have length larger than n. Okay. So, what does it mean that if I again look at the n step Gramian, I have n step controllability matrix, I have n minus 1 b, right. So, what happens when I look at a time n or n plus 1 or so on, this does not really contribute, right. So, this is what it means, that it does not depend on time only when the intervals have length greater than or equal to n. So, after n, I think any of those computations will not lead us to anything. But whereas if what happens if this interval is less than n, if k1 minus k0 is less than n. So, let us check with the help of an example. Okay. So, let us say I have a system in R2, xk plus 1 is a xk plus b uk, where a is 0 1 1 1, B is 0 1. Okay. Then the controllability matrix, which is B times AB, is 0 1 1 1, and the rank is 2 here, you can check that easily, and therefore the system is reachable. Which means that I can transfer from any state x naught to any other state x 1 in 2 time steps. Okay. Now, how do I let us say I have x 1 as some vector a b and x naught is such that this is a naught b naught. Okay. Now, I want to compute what are the control inputs that will steer the system to any other point in the state space. Okay. So, again we just look at x at 1 is a, x at 0 plus b u at 0, x of 2 is a, x of 1 plus b u of 1, this is a square x x naught plus a b u naught plus b times u 1. Okay. So, I can substitute. So, what do I know? I know what is x of 2 here is a comma b, this is the final state which I want to reach, and x naught is a naught and b naught. Okay. I know the matrices a, b and so on. So, I just substitute it over there to get the following. So, I can also write this as b times ab, that is with u1, u2 is x of 2. What is x of 2? That is the final state that I want to reach, ab minus a square x naught. Okay. What is a square? A square is 1 1 1 2. What is x naught? That is a naught and b naught. Okay. So, I know these two, therefore, I can compute my u to be u1, sorry, this should be u naught. u1 u naught is simply b minus 1 minus b 0 a minus a 0 minus b 0, okay, the minus here. Okay. Now, on the other hand, let me choose okay. So, let me just check the set of points I can actually reach in one time step, which means x of 1 is a x naught plus b u naught, and let me again just check, okay, what are the final states. X 1 is a b, x naught is a naught and b naught. Okay. In this case, I just do this rearrangement, x 1 is a b minus a, what is my a is I just get this here, a is 0 1 1 1 times x naught. What is x naught? Is a naught b naught plus the b matrix here is 0 1 and u naught. Okay. Here I can actually solve for u naught. For example, if x 1 is 1 comma 3 or 1 1 and 3 and x naught is 0 and 1. If I substitute this here, what I have, x 1 is 1 3 minus 0 1 1 1 0 1. Okay, sorry, there should be an equal to sign here. This equals to 0 1 u naught. Okay, so this implies that with u naught equal to 2, I can transfer the state from x 0, which is 0 1, to x 1, which is 1 3 in one time step. Okay. So, in this case, okay, what is the reachable subspace? Of course, when I compute C, I only look at B, right? Okay. So, the reachable subspace here is, if I can look at just R, I just compute the first term of the controllability matrix, which I just say that is C1. What is the first term of the controllability matrix? That is B, because I do not compute A square B anymore, right? Sorry, I do not compute A B anymore, right. So, this is the span of all vectors, span of 0 1, right, and in this case the transfer can be achieved in one time step. Okay. The same transfer can also be achieved in two time steps. Okay. And therefore, what do I have is, okay, we just go back to what we were saying here, right. So, in the discrete time case, the notion of controllability does not depend on time only when it is greater than n, right. But what if it is, what if the intervals are of length less than n? I still have a reachable subspace, but this reachable subspace will just be a subspace of this image of C. Okay, but the reverse inclusion will not hold. That is easy to check, right. So, image of C will not be a subset of R, right. So, which means that there are some states which I can reach in less than n time steps. In this example, there are states, for example, from 0 1 to 0 3, which I can actually reach in one time step. Not, I do not exactly need two time steps. So, there is some reachable subspace, and that subspace is just classified by the span of C, because so how do we look at R, the reachable subspace? Reachable subspace, say k 0 comma k 1 was equal to the image of C. Okay. And if this was usually, because the way we compute C was B till a n minus 1 b. So, I am looking at k 1 minus k 0 being equal to n, at least it could also be greater than 1. But what if it is less than 1? I am just looking at one time step. So, R at k 0 comma k 1, where k 1, okay, or I will just do this k 0 plus 1. So, I am just looking at just this. So, this is image of B. Okay, that is what exactly I am doing over here. Right. Okay. So, the controllability tests and all are very similar in the discrete time case, that the rank of C should be equal to n. Okay, I will skip this proof. I will also skip this proof of the Lyapunov test for controllability, right. So, so this is again exactly the same, and we know now the reason why this matrix looks in this form. A transpose W A minus W is B B transpose. I will skip these steps, but it is just useful to know the result. So, I just conclude this lecture over here, and in the next lecture what we will see is, okay, so far we have asked ourselves of when is the system controllable, how do I test whether or not the system is controllable? An important question that we will ask is what happens if the system is not controllable? How do I even check? System being not controllable might mean that there are some modes which I cannot control or some states which I cannot control. How do I even identify those? So, we will do that with the help of what we call as a controllable decomposition. So, that is coming up in the next lecture. Thank you.